Hello everyone and welcome to our session. I'm Professor Harrison and today we are going to explore the critical choice between logistic regression and neural networks. We will focus on the theoretical foundations that guide model selection and algorithm complexity. First, let's look at logistic regression. It is a fundamental linear classifier. While simple, it is highly efficient and provides a clear baseline for understanding how features relate to classifications through a linear decision boundary. In contrast, we have neural networks. These are known as universal function approximators. By using layers and nonlinear activation functions, they can capture complex, high-dimensional patterns that linear models simply cannot see. As this visual comparison suggests, the best model isn't always the most complex one. The central question for any data scientist is understanding exactly when the added complexity of a neural network is justified by the data. To guide us, we'll keep the no free lunch theorem in mind. No single algorithm works best for every problem. By the end of this class, you'll be able to navigate the trade-offs between data size, interpretability, and computational cost to pick the right tool for the job. To pick the right tool for the job, as we discussed, we must first understand the fundamental architectural split between linear and nonlinear models. Here we are comparing logistic regression and the multi-layer perceptron. Let's start with logistic regression on the left. Think of this as the simplest possible neural network, one that contains no hidden layers. As you can see in the formula, we take a linear combination of inputs and pass them through a sigmoid function. This creates a global linear separator. Because it's a single-layer architecture, its decision boundary is always a straight line or a flat plane. It is highly efficient and interpretable, but it can't solve problems where the data isn't linearly separable. Now, contrast that with the multi-layer perceptron, or MLP, on the right. This is where we introduce depth to capture complexity. In the MLP, we have multiple hidden layers. The activation of one layer becomes the input for the next, allowing the model to learn hierarchical features. These hidden layers enable the model to form nonlinear decision surfaces. It can essentially curve the boundary to fit complex patterns that a straight line simply cannot reach. Next, we'll see how these boundaries look in practice. In this simulation, we'll observe how different models learn to separate data points using decision boundaries. Let's start with logistic regression. Notice how it creates a straight line to separate these linearly separable points. When we switch to a circular distribution, a simple linear model like logistic regression struggles because it cannot bend the boundary. By switching to a neural network, the model can now learn nonlinear patterns to wrap around the circular data. You can increase the complexity of the neural network by adding more hidden units, which helps capture more intricate patterns. For a highly complex spiral dataset, we need more hidden units and a higher learning rate to converge on a solution. Click the Start button to watch the model iteratively adjust its decision boundary during the training process. Now that we've visualized how decision boundaries are formed, let's address the practical question. When should we actually choose logistic regression over a complex neural network? In many real-world scenarios, simpler is indeed better. First, consider your dataset size. When working with small datasets, logistic regression is significantly less prone to overfitting. A neural network with thousands of parameters can easily memorize small amounts of data, whereas LR's linear constraint provides a necessary regularization effect. Next is interpretability. Logistic regression provides clear weight coefficients for each feature. If you're working in a regulated industry like finance or healthcare, being able to explain exactly why a model made a specific prediction is often more important than a tiny gain in accuracy. We also have to think about computational efficiency. Logistic regression is incredibly fast to train and requires minimal resources for deployment. In production environments where latency and cost are key, the efficiency of LR is hard to beat. Finally, always use it as a solid baseline. Before jumping into deep learning, establish a performance floor with logistic regression. If a complex model doesn't significantly outperform this simple baseline, the added complexity is likely not justified. Leo, you're often skeptical of over-engineering solutions. How do you feel about this baseline-first approach? Now that we've seen where logistic regression shines, let's explore the conditions under which neural networks truly dominate the landscape and become the preferred choice for data scientists. The first major win is data scalability. While simpler models often hit a performance ceiling, neural networks maintain a performance trajectory that continues to improve as you feed them massive amounts of training samples. Secondly, deep learning is the undisputed king of unstructured data. For tasks involving raw images, audio files, or natural language text, these architectures can interpret complex patterns that traditional models simply cannot handle without significant pre-processing. We also see a huge shift in the workflow thanks to automated feature engineering. Instead of a human expert manually crafting features, the hidden layers learn to represent the data themselves, identifying intricate features that are often too subtle for us to define. Lastly, as we saw with our earlier look at decision boundaries, deep networks are built for nonlinear modeling. They can solve highly complex problems where the relationship between input and output is far from a straight line. Now that we've explored both sides of the coin, simple linear models and deep neural networks, how do we actually make the choice in a professional setting? This decision matrix is your roadmap for that strategic reasoning, helping us move beyond just picking the coolest model to picking the right one. Take a look at this comparison table. We aren't just looking at accuracy, we must balance it against interpretability, data requirements, and the compute power available. As Nora might emphasize in her notes, a model that is slightly more accurate but requires 10 times the data and compute power isn't always the most efficient choice for a project. Strategic reasoning requires us to look at the why behind our selection. It's often a trade-off between the transparency of a white box and the complexity of a black box. For instance, regulatory needs often dictate our path. In many industries, you must be able to explain a model's decision to an auditor. This is where white box models like logistic regression win because of their inherent auditability. Ultimately, the domain plays a massive role. Finance and healthcare prioritize interpretability to manage risk and ensure safety. However, in fields like computer vision, we usually prioritize accuracy and accept the complex nature of neural networks. Keep these trade-offs in mind as we head toward our final assessment. Now that we've completed our final assessment, let's wrap up today's session with some essential best practices and takeaways. We've covered a lot of ground, from the basic architecture of logistic regression to the complex layers of neural networks. First, always remember Occam's razor. In data science, if two models perform similarly, we should prefer the simpler one. As we discussed when looking at decision boundaries on page 3, a simpler model is often more robust and much easier to explain to stakeholders. Practically, I recommend a hybrid approach. Never jump straight into deep learning. Always establish a logistic regression baseline first. This gives you a performance floor and helps you determine if the extra complexity of a neural network is actually adding value. To summarize our use cases, use logistic regression for structured data and when you need to understand the why behind a prediction. Turn to neural networks for unstructured data like images and audio, or when you have massive data sets where nonlinear relationships are key. I've listed some resources here for further learning, including the documentation for scikit-learn and PyTorch. These will be invaluable as you start implementing these models in your own projects. You've all done a fantastic job today. From analyzing activation functions to building decision matrices, you've gained the critical thinking skills needed to navigate the trade-offs between these two powerful algorithms. Great work, everyone.